Hello, class. Welcome to week 6. So this is the last week of new material, although I will, of course, continue after this responding to your questions with office hour videos and various other such things to help you get through the end of the semester. But this week we're going and talking about optimization. So optimization problems will look like this. So in this episode, we'll do a bunch of problems that involve building fences, or we'll say something about what's the largest or the smallest, and then some various constraint. And we'll do a variety of these this week. And we'll talk about the general strategy for approaching this kind of question. So here the question is, we have 120 feet of fencing, and we want to build a rectangular fence. And the question is, what's the largest fence that we could build, given that? Okay. So I want to show you a bunch of the fences that you could build. So remember, we have 120 feet of fencing. So here are a bunch of different fences that use 120 feet of fencing. So for example, this one is 20 by 40. And so 20 plus 20 plus 40 plus 40 is 120. And this one would have, well, 20 times 40, which is 800 feet squared as area. I could go for a really oblong fence and make it 59 feet wide by 1 foot high. That still uses 120 feet of fencing, because 59 plus 59 plus 1 plus 1 is 120. But it encloses only 59 square feet of area. So you'll note this fence is way worse than this fence up here in terms of the area it encloses. And indeed, you might notice sort of like the more oblong the fence is, that is, the less square it is, or the further it is from being square if you prefer, the lower the area seems to be. And so at least of these 5 fences that I happen to have drawn for you, the best one seems to be this square one. But we'd like to know if there's actually a better fence out there or not. So we want to try and set this up. But we expect, at least from this example, maybe this is the best or maybe it's close to the best. We'll find out. So all of these problems are going to come down to finding 2 things and using them. So we have a thing to optimize. And then we have a constraint. Okay, and so in all of these problems, the first thing you should do is identify what is the thing that you're trying to optimize and what is the constraint. Okay, so the thing you're trying to optimize, that's the thing that you want to find the maximum or the minimum of. So in this case, the question specifically says largest area. So the thing I'm trying to optimize here is the area. But then I'm constrained by something because, of course, if I was just trying to build the largest rectangular area and I had no constraints, I could build a fence that was 1 billion miles by 1 billion miles, and it would have an enormous area, but I can't do that because I'm constrained that I'm only allowed to use 120 feet of fencing. So we have our thing to optimize, which is area, and we have our constraint, which is fencing. And I want to write down formulas for both of these, but in order to write down formulas for both of these, I need to make a picture. And so this is a bunch of pictures that I showed you before. I want to make a general picture, so I'm just going to draw a rectangle here, and I'm going to label these sides x and these sides y. And I want to figure out what x and y are in the best possible fence. Okay, so my area here, I'll note that that is x times y, because the area of a rectangle is the length of the rectangle times the width, or whatever, height times base, whatever way you want to think about this, it's x times y is the area here. And the fencing, well, I have 120 feet of fencing, and that's going to be x plus y plus y. Or 2x plus 2y. So that will give us our constraint. So I'm going to use these two pieces to solve the problem. Now, the key idea that underlies all of this is that the max value of a function happens at either a place where the derivative is 0 or an endpoint. Okay, and the same is actually also true of the min value. So we know, roughly speaking, how to go about finding these things. This all comes back to, remember our friend from earlier in the course, the closed interval method. And this is exactly what the closed interval method says. Okay, so what's our problem here? Well, we know this thing happens for a function. What we're missing so far is a function. You might also question what the words endpoint here mean, because I didn't explicitly say anything in this problem about what the endpoints are. But there's an implicit endpoint here that this x, well, it can't be less than 0. And so, in fact, this x actually you can figure out. It's always between 0 and 60. And really, you can probably convince yourself that probably the maximum value doesn't occur when x is 0 or 60. Where did the 60 come from? When x is 60, if I'm using 120 feet of fencing, that's when y is 0. So likewise, y is also bounded in this closed interval between 0 and 60. Okay, so how are we going to fetch our function out of this to apply this to? And so here's what we're going to do, and this is always going to be what we're going to do. We're going to use the constraint to write the thing to optimize as a one-variable function. Okay, so what do I mean by that? Well, this technically, in a sense that you'll find out about if you keep taking math courses, this technically is a function. It's just a function that has two variables in it. Namely, it has the variable x and the variable y. And given that if you look at the name of this course, it is something like single variable calculus, you can guess we can't have two variables floating around. So I want to reduce this to having only one variable, and I'm going to do that by using this constraint. So what I'm going to do that is I'm going to solve this constraint for y. Okay, so I'm going to write down 120 equals 2x plus 2y. And then I'm going to solve this. So I'll get, that means that 2y is 120 minus 2x, which means that y is 60 minus x. Okay, and that is our majestic relationship between y and x. And I'm going to use this to rewrite my thing to optimize, namely my area, which I've written previously as x times y. My area is x times y, but y is 60 minus x, so this area is x times 60 minus x. And when I said one variable function, that is what I was looking for. This now only involves x. So I have my a of x is x times 60 minus x, and I want to find the maximum value of this function. Subject, again, to the fact that I need my interval here to be x is between 0 and 60. Okay, so let's rewrite a of x is 60x minus x squared. And remember, again, it either happens at a place where the derivative is 0 or the endpoints. So let's take the derivative. We'll set that equal to 0, which will give me 2x is 60, which will give me x is 30 feet. Okay, and so that means that now my best possible fence happens either when x is 30, when x is 0, or when x is 60. So just like in the regular closed interval method, because that's really all we're doing here, I can calculate a of 0, a of 30, and a of 60. Now, it's not so difficult to see that a of 0 is 0, and likewise a of 60 is 0. So those are definitely not the place where my maximum occurs. But a of 30, this is actually 900. And so that tells me this is really my best possible fence. So that happens when x is 30 feet. So when x is 30 feet, I need to ask my question, hey, what's y when x is 30? And to do that, I go back over to here. Namely, I remember that y is 60 minus x. So 60 minus 30, that's also 30. And so we find that our best fence happens when we have a 30-foot by 30-foot rectangle whose area is 900 feet squared. Namely, if we look back at our sheet of paper where we looked at all the examples, this actually was the best fence. Okay. In the next video, I'm going to do a couple more examples. We're going to put small twists on the kind of fence that we're building. But until next time, be well.